All right, good morning, everyone. Let's get started. In the previous class, we started discussing the achievability part of the channel coding theorem. We discussed the channel coding problem in some detail, and I also talked about how do you choose different encoders and decoders. Right? So we had a long discussion about how do you choose a good decoder for a given channel code, and we saw that the most common decoders which are analyzed uh, theoretically are the following: the map decoder, which is really the best if you want to minimize the probability of error for a given code; the maximum likelihood decoder, which is the same as map if the input is uniformly distributed. But both of these are generally hard to analyze, at least information theoretically. So we instead look at a slightly worse decoder, which is the joint typicality decoder. The joint typicality decoder does the following: it declares a particular message. So given a particular received sequence, it says that message W was transmitted if the Wth code word is the only one which is jointly typical with respect to the received sequence. If not, it just gives up. All right. But for certain other problems such as the AWGN channel or for even the BSC, we can define other decoders. So one commonly studied decoder is the minimum distance decoder, and the other is the bounded distance decoder. And we discussed at length the geometric interpretations of each of these, what exactly each decoder does for the specific case of channels where you have a distance embedded in the alphabet. All right. So in this class, we will discuss the proof of the achievability part of the channel coding theorem, and we'll add a little more. We'll add another level to the statement, in that we will also study the problem with an input cost constraint. So it is not just the problem is not just to transmit across the DMC with an arbitrarily low probability of error, but the input sequences that you can transmit have to satisfy some kind of a cost constraint. Think of this as a power constraint, right? And we'll allow for general costs. In particular, we'll say that every code word xn should satisfy the following cost constraint. For some function alpha, we should satisfy summation I going from 1 through n. Alpha of xi should be less than or equal to n times beta. Now you can have multiple cost constraints. That is also okay. And even in such scenarios, we'll see what the capacity is, and we'll derive the achievability part of the channel coding theorem for this particular scenario. Okay. So before we proceed, are there any questions from the last class? Okay, so recall what the channel coding problem is. We have a message W, which consists of kn bits, and we want to encode this to a code word xn. So the encoder is a map which takes a message of length kn into a code word of length n, where each xi comes from the input alphabet script x. This is transmitted across a DMC, and the DMC outputs some random yn conditionally dependent on xn. And we want to also design this decoder such that the decoder outputs an estimate of the message. So it's another binary sequence of length kn, and we want to ensure that the probability that w hat is not equal to w is vanishingly small. Okay. And And now we're imposing this constraint that every transmitted sequence xn must satisfy the property that summation I going from 1 through n alpha of xi should be less than or equal to some n times beta. So the cost function is some function from the input alphabet to the set of positive or non-negative real numbers, right? And we want to ensure that this cost constraint is satisfied. Now it turns out that the capacity of this channel, now you know that if there is no cost constraint, then the capacity is just the maximum overall possible input distributions of the mutual information between x and y. This is assuming that there is no cost constraint. We've already seen this in a previous course, right? But now if we have this additional cost constraint, then this is the maximum over all possible input distributions, so it satisfies a certain property. And the property they need to satisfy is that the expectation over x of alpha of x should be less than or equal to beta. All right. So this turns out to be the capacity of the channel. And now we will show that you can indeed construct. So there is a sequence of codes such that asymptotically the rate can be made arbitrarily close to the capacity. And also asymptotically, the probability of error is vanishingly small. It in fact decays exponentially in n. Okay. So our goal will be to show this. And in fact, handling this additional cost constraint, we'll see turns out to be not very complicated at all. It's just one extra step that is required when compared to the standard proof of the normal channel coding theorem. All right. So the technique that we will use to prove this particular statement is using random codes. Now, as I mentioned, so the goal is to see what the best code can do, right? So ideally you want to, so given a particular rate r or given a particular kn for a given n, you want to know what is the minimum possible probability of error or the minimum average probability of error that which is achieved by the best possible code. So you try to minimize overall possible encoders and decoders of the probability that w hat is not equal to w. Right? But this is hard to compute. This is hard to it's even hard to get an accurate bound on what this minimum probability of error is. So what we do is we instead try to find the average probability of error averaged over a random code. So this is obviously going to be less than or equal to the average probability of error, where now you choose the code at random. Right? You choose a random code and you fix a particular decoder and you analyze the expected probability of error. And if you can show that this is, and now we will show that as long as r is less than this mutual information minus some suitable epsilon, this probability of error in fact decays exponentially in n. So this is less than or equal to e to the minus gamma times n for some constant gamma. All right. So for this we need to define what the random code is and how do we choose the random code. Right? And the way we will do it is pretty natural. So look at all possible message sequences w. So we have 0, 0, 0, 0. So kn bits. And so on. All right. So this is message number 1, this is message number 2, and similarly this goes on up to 2 to the kn. Right? So for each of these, we need to define a suitable code word. So let me call this x of, so this is x1 of 1, x2 of 1. So for message 1, we have xn of 1. For message 2, you have xn of 2. Similarly, for the 2 to the knth message, you have the code word is xn of 2 to the kn. Right? This is the code word corresponding to the first message. This is the code word for the second message, and so on. x2 of 1, x1 of 2, x2 of 2, xn of 2, and so on. Right? And so now we are going to choose a random code, which means that for each message, the code word will be randomly chosen. So for a particular realization, we'll get one particular code book, but and we'll basically analyze the average probability of error across all possible code books. Right? And the way we will choose this particular each code word is in the following way. Each xi of j is going to be chosen independently of each other and randomly according to the distribution px. Okay, so you fix a px which gets you close to this. All right, so firstly you fix a px such that the mutual information between x and y is less than or equal to is let us say equal to this capacity c minus some quantity epsilon, and the expectation of alpha of x is equal to the beta minus say epsilon. Okay, so basically we're going to choose px. Let's say I'll choose it in a slightly different way. Beta by 1 plus epsilon, let us say. So we'll see why I'm choosing this beta over 1 plus epsilon. Okay, so you choose a px such that this mutual information is equal to c minus epsilon, and the expectation over alpha of x is beta over 1 plus epsilon. And now you set kn to be, let us say, I of xy times n. Okay, so you're operating at a rate equal to c minus epsilon, and the expectation over alpha of x is beta over 1 plus epsilon. Okay, so that fixes all these numbers. Now you generate each of these entries. So basically your goal is to generate this table of code words. Each entry of this table is generated IID according to px. Okay. So you generate each xi of j. So the ith entry of the jth code word according to px. Okay, so maybe so in the case of the BSC with some probability, so in the case of the BSCP, and if you don't have any input constraints, the distribution which achieves capacity is the uniform distribution, and in that case you can just generate you basically generate each of these entries according to Bernoulli half. Okay, So once you generate this, so for a particular realization, you get one particular code book, right? So this gives you a code book C. So the code book C is basically just a table of code words, right? So this is generated upfront before even transmission. Okay, so you generate a particular code book. This code book is shared between the transmitter and the receiver. Both the transmitter and the receiver know the code book. They know the code book, which means that they know this entire table. Okay, and what does the encoder do? So the encoder, given this particular, now that you have generated a code, the encoder does the following. Given that you want to transmit the ith message, or let's say the jth message, you just transmit the jth code word. All right. So let us say that you want to transmit this. So the actual message is this particular sequence. If W is this particular sequence, then what does the encoder do? It just outputs this particular code word sequence. Right? So maybe one realization is 0 0 1 0 1 1 0. Maybe this is code word 1. Maybe this is code word 2. This is code word 3, and so on. So if you want to so if the actual message is this, then the transmitter sends this particular code word across the channel, one symbol at a time. Okay, and this code word is transmitted across the channel. The receiver gets some particular yn. Okay, so this is transmitted. Okay. So let me just quickly recap. So we're generating the code book at random. You generate one random code book and you analyze the performance of this particular code book. Okay. So you generate this code book at random. And now that you've generated all the code words, this is given to both the transmitter and the receiver. And the transmitter, if it wants to transmit the jth message, it just sends the jth code word across the channel. Okay, and the goal of the receiver now is to identify which code word was transmitted. Now, one thing to note is that since these code books are generated independently at random, there is a possibility that two messages could correspond to the same code word. There is some probability of that happening. Although the probability is small for large enough n, there is still a possibility of a collision, and note that this will cause an error. But that's okay. It doesn't matter. We will count that as an error later. All right. But this is the code generation. This is the code book generation process, and this is the encoding process. You just have the table. You just transmit the code word which is there according to that particular table. Okay. Is the encoder part clear? Yeah. So this is what the encoder does. Now let's see what the decoder does. As I mentioned, we'll analyze the typical set decoder. So what does the decoder do? You say that W hat, the estimate, is equal to W if there is a unique message W such that xn of W is jointly typical with respect to the received sequence. right? Otherwise, you just output the all zeros sequence. Okay, so once again, if you look at this particular diagram over here, so basically, what does random codebook generation mean? You just pick 2 to the kn points at random uniformly. Let's say, actually, you generated IID according to px, and that specifies these blue dots. That blue dots are fixed by that, right? Now, if you want to the transmitter wants to send, say, the jth message, which implies that you just transmit the jth code word, and once you transmit the jth code word, you receive some
Sir,
sequence in this particular space. Yes, question.
sir, like the random codebook generation, like each codebook would be the generate for each message, right? Like for each message,
Correct.
we will generate like a random codebook, right?
Correct. Correct.
Okay, so like
No, for each message you don't generate. So for each message, so this is what you do. So there are two processes. One is actually the encoding process. Now, even before you see the message, right? You first generate a code book.
okay, okay,
Okay, you randomly generate a code book, and then now once you have generated the code book, this is shared between the transmitter and the receiver.
okay. So okay,
Okay,
okay. So yeah, so before like entering to the problem, the codebook is fixed, but it is random.
exactly. So the code book is fixed upfront.
Okay, okay,
Okay, and then you get messages. You transmit these messages across the channel by encoding them.
okay.
Okay, so in some sense, this whole idea of random codebooks. So note that the codebook is not generated after you see the message or at the time you see the message. The codebook is generated even before that. Right? So, given that maybe this code word is transmitted, maybe you receive some sequence in space. Maybe this is the received sequence. The joint typicality decoder just checks if there is exactly one code word which is jointly typical with respect to this. All right. So in this case, it is jointly typical with respect to this code word, and the decoder just declares this to be the transmitted message. If the received sequence lied were such that it is jointly typical with respect to two different messages, then it basically corresponds to an error. It just declares, okay, I don't know what to do. All right. Or if it is not typical with respect to anything, with respect to any code word, then again the decoder doesn't know what to do and will just count that as an error. Right? It's possible that it is not an error, but for the purpose of analysis of the probability of error, we'll consider that as an error event. Okay, so this is how the decoder does for a given code book. Right, so you're fixing the code book upfront. So the decoder already knows what the code book is. Okay, so this is how the encoder and the decoder work. The encoding is just a lookup table, and the decoder is a typical set decoder. And this lookup table has been generated randomly. Okay, and our goal is, so for a given code book, we'll see, we can't really, for a specific code book, it will be hard to analyze what the probability of error is. But basically what we're doing is we're analyzing the probability of error over all possible code books. All right. So given this, our goal is to understand what the probability of error is, right? And the probability of error that, so let us formally see what the probability of error is. Okay, so what we're interested in is the average probability of error, 2 to the kn, summation over all possible messages w, uh, to the kn, the probability that w hat is not equal to w, right? So let me put this here. Yeah. So this is the average probability of error, given that W was transmitted, given that W was transmitted, right? So for a particular code book, this is the probability of error, right? So, or more formally, this is equal to the summation over all W, the probability that whatever. So let us call this. So I'll define an error event for a particular message W. So let us say that W was actually transmitted. So the error event corresponding to W is that you receive yn such that okay, so anyway, let us see what the exact error event is just a little bit later. But let us say that for a given W, error occurs given that W, the message W was actually transmitted. Okay, so some error event happens, and that is the error event corresponding to W. And this error event depends now can depend on many things. For a given code book, having fixed a particular code book, the only source of randomness is in the channel, right? So this is the probability Py given X for that EW occurs given a particular code book and that W was transmitted. The probability that a particular message W was transmitted is 1 over 2 to the kn, because we're assuming that all messages are equally likely. Okay, so this is the probability of error for a particular code book. Okay, and the probability of error averaged over all possible code books is basically the expectation of this, which is the summation over all possible code books, the probability of choosing a particular code book times this probability, W, the probability. So here the probability is over the codebook generation process, whereas this probability is with respect to the channel, the randomness introduced by the channel. And this is the probability that the message W is in error given a particular codebook and that W was transmitted times 1 over 2 to the kn. Okay, so now what we're going to do is we're going to interchange this basically the order of summation. Right? It's basically just a mathematical step. So you first sum over all possible W and times the probability that the message W was transmitted, sum over all possible code books, the probability that this particular code book was chosen, C times the probability of that the message W is decoded incorrectly given that you choose a code book C and W was transmitted, right? And now what we're basically going to do is we're going to analyze this particular quantity. Okay. So we'll show that given a particular message W, the probability of error is vanishingly small. This probability over here is vanishingly small for any given W, which implies that, so let's call this PE AVG of W, and we'll show that for any given W, this is vanishingly small. And if this quantity is less than or equal to 2 to the minus or whatever e to the minus gamma times n, then this overall probability of error is also less than or equal to e to the minus gamma times n. Right? And since we're generating each code word identically, right? So each code word is generated independently and identically at random. It suffices to just look at the average probability of error, given that maybe the first message was transmitted or the all zeros message vector was actually transmitted. Okay, so now what we'll do is we'll study this particular quantity and show that as long as R is less than the capacity, this probability of error is vanishing in. Okay, so far so good. Any questions?
Sir, you are not audible, I think.
Uh,
Yes, sir, you are not
Yeah.
audible, sir.
am I audible now?
Yes, sir.
Okay,
Yes,
great,
sir.
thanks. All right. So now what do we want to see? We want to analyze what the probability of error is. So in other words, we want to see what are all possible error events that could occur given that you transmitted the first message. And we want to find out what is the probability of those events occurring. Okay, so note that we want to satisfy certain constraints. We want to satisfy an input cost constraint, and we need to ensure that the message was decoded correctly, right? But since we're generating the code words in an IID fashion, it could be possible, it potentially with some probability, it is possible that the code word that was generated for that particular message does not satisfy the cost constraint. Okay, and that will be treated as an error. Okay, so because after all, you cannot transmit something which does not satisfy the cost constraint. So the first source of error is that, so given that the message that needs to be transmitted is the all zero sequence, or basically this is the first message, the first source of error is that xn of 1 does not satisfy the cost constraint. So the cost constraint is that I going from 1 through n, alpha of xi of 1 less than or equal to n times beta. Okay, this is one source of error. And in this case, you cannot actually transmit this code word because it does not satisfy the power constraint or the cost constraint. Okay, and we want to ensure that this does not happen, right? So this is one source of error. The second source of error is now a decoding error. So this is what can happen, what can go wrong at the encoder. Now at the decoder, either the received sequence, so yn, is not jointly typical with respect to xn of 1. So xn of 1 and yn are not jointly typical. But we know that this doesn't, the probability of this happening is very, very small. Note that xn, so xn of 1 is generated IID, it is transmitted across the channel, and yn is obtained by passing xn through the DMC py given x. So they're jointly distributed according to pxy and their IID. So the probability of them not being jointly typical is vanishing in n. We know that. So this source of error is not too bad. Right? So the third thing is that so this is one error which basically corresponds to the property that the received sequence is not in any of these balls, right? It lies somewhere outside this particular shell. So given this particular transmitted sequence, the received sequence does not lie in this particular shell. So that is the source of, that is the second type of error that can occur. The third type of error is that it lies in multiple shells. That is, it lies somewhere in this particular region. Okay, so that is the third source of error, is that it is jointly typical with respect to some other message. Yn, these two belong to, so yn is actually obtained by passing xn of 1 through the DMC, but some other xn of j and yn are actually jointly typical for some j not equal to 1. Okay, so these are the possible sources of error, right? And you should convince yourself that these are the only sources of error. So if none of these three things happen, then of course the code word satisfies the cost constraint, so it is actually transmitted across the channel, and the received sequence the received sequence is jointly typical with respect to xn of 1, and it is not jointly typical with respect to any other code word, which implies that it is decoded correctly. Okay, so everything happens. So if all is good if none of these three events happen. So as long as we can show that these three events happen with a very small probability, we are good to go. We know that the probability of error is vanishingly small. Okay, so the probability of error PVG of 1, this is, I claim this is less than or equal to the probability of event 1 occurring plus the probability of event 2 occurring plus the probability of event 3 occurring. Why is this true?
Because the events are disjoint.
They're not disjoint, right? It's possible that that these two could happen. It could be possible that yn is not jointly typical with respect to xn, and it is typical with respect to some other j, or either way.
So the union bound.
Exactly. So it's just the union bound. So this just follows via the union bound. Now, okay. So now let's look at each of these three error events. Right? So what is the probability of one occurring? So the probability that one occurs. Right? So this is the probability that that alpha of xi of 1 is greater than n times beta. So summation I equal to 1 to n alpha of xi of 1 is greater than n times beta. Okay, so how will we bound this? Any suggestions? So here's a hint. All the xi's are IID, right?
Sir,
According to PX.
can we use Chernoff bound?
Exactly. So you can use Chernoff bound. So how would you use it? Let's call this, let me call it chi I. Okay, alpha of xi of 1 is chi I. So what is the expected value of chi I? So by design, what is this equal to? Let's go back.
Beta by 1 plus.
Correct. So we've chosen a px such that the expectation of alpha of x is beta over 1 plus epsilon. Right, so this is beta over 1 plus epsilon. All right, so what we want is the probability that summation I going from 1 through n chi I is greater than n times beta or n times expectation over chi times 1 plus epsilon. All right, and just by Chernoff bound, this is less than or equal to e to the minus some constant times, well, in fact, I'll do it slightly better. So this is less than or equal to n times epsilon square times the expectation of chi, 1 plus epsilon by 3. Right? So this quantity, I mean, irrespective of what epsilon is, and irrespective of what beta is, as long as beta is something strictly positive, this quantity is vanishing in it. Right? It's exponentially decaying in it. So that is fine. So the first event is okay. What about the second event? So it is a probability that xn of 1, yn are not in the typical set. Right? So what is this? Less than or equal to? Does this decay exponentially in n?
Yeah, it is like at the most 2 to the power minus n times joint entropy of xn and yn.
Sure. Yeah, fine. So this is something. So it doesn't matter what this exactly is, but this is less than or equal to 2 to the minus n times something. All right, and that is because the xn of 1 and yn are IID pxy. So this probability, okay, fine. So let's do it more carefully. So this is less than or equal to, so probability that they're not, but it's not less than or equal to 2 to the minus n times h of x comma y. It's actually 10 to e to the minus n times some delta of epsilon, right? Because you're not looking at a specific yn, or you're not looking at a specific, so for a specific xn, or a specific typical xn, the probability that these two are, the probability of realization of a particular xn yn is less than or equal to 2 to the minus n times the joint entropy, right? But the probability that a random pair of sequences, IID pxy sequences, are not in the typical set actually vanishes as 2 to the minus n times some epsilon, some constant times epsilon square. Right?
So sir, if it is not a random, if the code word is not randomly generated, then it will be like 2 to the power minus n times h joint entropy,
Yeah,
right?
or more specifically, the probability of a particular xn yn in the typical set, that is 2 to the minus n times h of x comma y, right, roughly. But this is, what is the probability that it does not lie in the typical set at all?
Okay.
And these are two different quantities. So we have seen this before, right? So I guess that was it. Yep. Yeah. So the probability that x and yn are not jointly typical is less than or equal to e to the minus some constant times n epsilon square. But so for a given pair of sequences in the typical set, the probability of seeing that particular pair of sequences is roughly 2 to the minus n times the joint entropy.
Got it.
Right. Okay, so now we've bounded two of these probabilities, and now as long as we show that the third probability is also vanishingly small, we're done. Okay, so to prove the third quantity, we will prove the following slightly more general result. We'll call it the packing lemma, and it says the following. So suppose you have some joint distribution pxyu. So I'm also introducing a new random variable u, and let us suppose that yn and un are id pyu. Okay, and I generate m random variables, m random vectors id according to px given u. Now conditioned on the un sequence, xn and yn are independent. So xn and yn independent given un. Xn is independent of so xn of I is independent of yn conditioned on un. So given a particular un, xn of I and yn are conditionally independent for all I going from 1 through 1, 2, 3 up to whatever 2 to the nr. So I'm generating n sequences, 2 to the nr sequences, and all of them are generated IID px given u and conditionally independent of yn, which is the exact situation that we have here, except that we don't have a un. All right. So yn is the received sequence, which depends on xn of 1, really, or let's call it xn of 1, and xn of 2, xn of 3, and so on up to xn of 2 to the nr are all are actually independent of yn, right? And now the question is, okay, what is the probability that any of these other code words are jointly typical with respect to yn? Okay, so the probability that xn of m and yn and un are all jointly typical for some m, so this is vanishing in n. Okay, so that's the claim. But this doesn't happen for all possible R. This happens as long as R is strictly less than the mutual information between X and Y given U minus some delta of epsilon. So as long as you're not generating too many sequences, the remaining sequences are going to be atypical with respect to Yn with high probability. That's the claim. Okay, and basically what in the context of this particular channel coding theorem, what we're saying is that as long as, so you're generating all the other code words independent of the first code word, the received sequence depends only on the first code word. So as long as there are not too many other code words, they're not going to be jointly typical with respect to Yn with high probability. Okay, and this lemma is again easy to show. So the so anyway, let's go to that a little bit later. I'll prove this later, but let's complete the proof of the channel coding theorem, assuming that this packing lemma is true. Okay, so the probability of 3 is less than or equal to, so this is equal to the probability that xn of whatever j and yn. So the received sequence is jointly typical with respect to some other code word for some j, which could be either 2 or 3 or whatever, 2 to the nr, or in this case 2 to the kn, right? So again, since all the xn's are generated IID and they're independent of yn, all right, so this, just by the packing lemma, is less than or equal to e to the minus some constant, some delta prime of epsilon, as long as kn is strictly less than I of xy, or in this particular case, it's less than or equal to, it's less than c minus epsilon. Right? So as long as this happens, this probability is vanishingly small in n times delta of epsilon. Right? So the probability of this occurring is vanishingly small in n. The probability of this occurring is vanishingly small in n. And this happens irrespective of what the rate is. So this third quantity also vanishes in n as long as the rate is not too large. It is less than ixy. Okay, and that really completes the proof of the achievability part. So we have 3 sources of error, and each of these error events can happen with exponentially small probability. So the overall probability of error is also decaying exponentially in n. All right. So all that remains is to prove this particular packing lemma. All right. And this is again, it's just a consequence of the joint typicality lemma. All right. So we want to see what is the probability of this happening. So the probability of this happening just by the union bound is less than or equal to m going from 1 through n of the probability that xn of m yn un are in the jointly typical set right? This is just union bound. Sorry, 1 through 2 to the NR, right? And just by the joint typicality lemma, this probability is less than or equal to 2 to the minus n times the mutual information between x and y given u, equal to 1 to 2 to the nr times 2 to the minus n times I of x, y given u minus some delta of epsilon. All right. So this is simply 2 to the nr times 2 to the minus n times the mutual information epsilon. So as long as r is less than this particular quantity, this is less than 2 to the minus some n times delta prime of epsilon, as long as the exponent is negative, right? As long as r is less than, so it is 2 to the n times r minus n times r minus, sorry, this minus r. So as long as r is strictly less than I of x, y given u minus some delta of epsilon. All right. So again, a very quick recap. We wanted to show that there exists a sequence of codes for which the rate approaches this capacity and the probability of error is vanishing in n. Right? So what we did was we generated a sequence of random codes, and for that sequence of random codes, so the random codes were generated in an IID manner, and for this sequence we analyzed the probability of error. Right? And the way we analyzed the probability of error was that was the following way. We saw that there are three possible error events that can possibly occur. One is that the cost constraint is not satisfied. The second is that the received sequence is not jointly typical with respect to the transmitted code word. And the third event is that the received sequence is jointly typical with respect to some other code word. So the first error event was bounded using Chernoff bound. The second event just so the second event was bounded just by using properties of jointly typical sets. And the third event was the probability of the third event was bounded using this packing lemma, which basically which in some sense what you're doing when you're employing this union bound, you're just looking at the pairwise probability of error. So if you look at each of these terms, this is the probability that the received sequence yn is jointly typical with respect to the mth code word, right? So this quantity is basically the probability that you transmit xn of 1, but then you decode it as xn of m. Right? So this is in fact the pairwise probability of error, the probability of decoding it as m, given that you're actually transmitting 1, and this probability is just given by the joint typicality lemma, and as long as r is not too large, the overall probability of error is also vanishingly small. All right. So once we show that all these three error events occur with very small probability, it also implies that the overall probability of error is also vanishing in it. All right. So any questions? All right. So really, to really understand the proof better, you should try to work it out on your own. Try to think about what the possible error events are, and also see how you would bound each error event. So we've seen a bunch of different lemmas, and the only way is to understand these better is to apply these results or these properties of typical sets a number of times. Right? That is the only way you will get comfort with using these properties of typical sets. All right. Any questions? Okay, so if there are no further questions, then we'll stop for the day.